Hello, people. Let's talk about multiple resistor circuits and applying Kirchhoff's rules. Two of them in particular, the loop rule and the junction rule. So here's a circuit with a couple of resistors. Let's name them R1 and R2. And here's a battery with a potential difference V battery. Now, what I'm going to do is draw this as a voltmeter measuring the potential difference of the voltage across that battery. And here is a voltmeter measuring the voltage across R1. Here's a voltmeter measuring the voltage across resistor R2. You'll also hear me say measuring the potential difference. Voltage and potential difference are the same thing. Now, what we're going to do in a few cases, in most cases where we analyze a circuit, is we're going to define the circuit's overall or total resistance. And what we're gonna call that its equivalent resistance. And so what we're sort of saying is that there is a circuit that has that same battery, but has one resistor of a resistance we'll call Req, or the equivalent resistance, and that circuit behaves on a very broad sense like this one behaves, in that it'll carry the same current. All right, so we're going to get to an expression for how we express, an expression for the equivalent resistance of some resistors connected in series. We'll get to that. And we're going to start by looking at what the loop rule says about this circuit. Well, the loop rule says that around any single loop of current, here is a loop of current, it says that the net V gain and the net V drop are the same. Now, what it really says is net V, the net voltage is 0, and there's a positive voltage across the battery, a negative voltage here, and a negative voltage there. So if we account properly for signs, then the net voltage is 0. I talk about the magnitudes of the gains and the drops. All right. So you can write this in a couple of ways. You can say, well, V battery minus V1 minus V2 is 0, or therefore V battery equals V1 plus V2. So here's our sum of the voltage drops. Here's our net voltage gain. Okay, now we can re-express these voltages using Ohm's law. Now, Ohm's law says that V equals I times R. So the battery voltage can be expressed as I through the battery times R through the battery of the, of the whole circuit. All right. So I'm going to call that, that's our Req. This is kind of our total, right? Total current, battery current, yeah, total, same thing. Total resistance, equivalent resistance, same thing. So that's our V battery expression using Ohm's law. V1 we simply write as, I1 R1. V2 we write as I2 R2. Now the junction rule, well, we're going to get in a little more specifics about what the junction rule says, but the junction rule is about current. And if we look at this single loop of current, well, there's the same amount of current everywhere. All right. Junction rule justifies that. But because this is one loop of current, well, there can't be different amounts of current in different places, because that would mean that more electrons got to a place than left that place. All right. So all these currents, I battery equals I1 equals I2, they're all the same amount of current. And thus, we can say, well, if these are all the same amounts of current, then each one of those terms can be divided by the same common factor. And what we're left with is this expression for the equivalent resistance of resistors connected in series. And it's just add them up. And if we had more than 2, well, we could add up however many we had that were connected in series. All right, so in this case, we have two resistors connected in series. If we know each of their resistances, we can find the circuit's total resistance by adding up each of the resistors. Fair enough. Now, once we have that, well, there's information we can gain from there. You know, if we knew V battery and Req, well, guess what? We know two parts of Ohm's law. We can then find the third. Oh, we could say, well, there's a current that's equal to V battery over Req, and then they say, oh, well, the currents are all the same. That means I know the current. So we can, you know, in many cases, starting with this step can lead us to some general information that we can then apply more specifically to different parts of the circuit. Okay, so series, equivalent, add them up. Okay, well, example. Here is a circuit with resistor R1, R2, R3, V battery. Let's call this V1. Notice I'm drawing these schematic representations of voltmeters in the way that you actually connect a voltmeter, and that is before and after a circuit element, or in parallel with that circuit element. So now what we're going to be able to do here, notice we've got a table that's going to allow us to list voltages, currents, and resistances at / through / of each of these elements. And we've got, you know, a row for the total, a row for element 1, for element 2, for element 3. And notice we have the resistances of each of those elements. So what we can do is say, well, I know the equivalent resistance of all these things. That's the sum of all of the individual resistors. So that's 100 ohms. All right. And so what we're saying is that at a pretty basic level, this circuit above behaves like this circuit with a 100 ohm resistor and a 25 volt battery. Well, how does that circuit behave? Well, in general, we could say that this circuit, we could say, well, I is V over R. This happens to be our total current and our total voltage, which is our battery voltage, and our total resistance, which is our equivalent resistance. So our 25 volts over our 100 ohms gives us a total current of 0.25 amps. So what we do with that is then we say, okay, well, let's see what that general information can help us find in a more specific, you know, looking at each individual part of this circuit. Well, what you have to know is there's the same amount of current everywhere in this single loop, right? What this says is, what 0.25 amps means is that, well, there are, I mean, quite literally, 0.25 amps, 0.25 amps means 0.25 coulombs per second go past this point, and 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 this point. And so what it says is whatever number of coulombs coulombs of charge get to a point per second, that number of coulombs must leave that point, because if they didn't, where did they go? All right. So we have to be able to justify that in this single loop where there's only one path that current could possibly be in, current everywhere in that path is constant. And then now we can apply Ohm's law to find the voltage across each of these individual resistors. We can say V1 is I1R1, 0.25 times 30, that's 7.5 volts. V2 is I2R2, 0.25 times 10, that's roughly 2.5 volts. And V3, of course, I3R3, 0.25, a quarter of 60 is 15 volts. If only I could tell if we're right. Gee, I hope we're right. Well, of course we're right, because look, 15 plus, you might notice that's a total of 10. 15 plus 10 gives us 25. The loop rule has held up. We know for sure we've done this right. Yay, us. Okay? This is perhaps the thing that people screw up the most in what seem like very simple. This is just a series circuit. Everything's so easy. People screw up that the currents are all the same. All right. That's kind of that's what you have to be able to. People are really good with this. Oh yeah, okay, I've got 3 resistors, add them up to find equivalent, no problem. I can find this, okay, great. And then boom, all of these have to be equal to that total current, because what else could they be? How could they be different? How could each of these things in the same single loop of current draw a different current? They can't. Okay, okay, and then again, our loop rule holds up because the net drop equals the net gain. We're in good shape. Here is a simple circuit with 2 resistors connected in parallel. In parallel means that there are multiple paths that current can take. Here's one path. That is one loop that current could follow, that a single electron could follow. Here's a second loop. There are multiple consecutive loops of current. All right. Now, let's name this stuff. Let's name this as V battery. Let's name this as R1. Let's name this as R2. Let's name this voltage V1. Let's name this potential difference, same thing as voltage V2. And then up here, I have a thing I can drag into place here and say, this is a meter I'm going to put right in the middle of that wire that's going to measure the current that goes through it. So this is going to give us a measurement of current 1, that's I1, current 2, I2. And then we could also have one here that measures the current prior to that split. So I'm going to call that I total. Now here's the thing about the loop rule. The loop rule, the first 6 words of the loop rule are super duper important. And those first words are around a single loop of current, dot, 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 net V gain equals net V drop, right? This has multiple loops of current. In each loop of current, there is a single resistor. So one loop says, okay, V battery equals V1. Should have done that in red, perhaps. The other loop says that V battery equals V2. All right, if this is, you know, a 10-volt drop, and we go around this loop, there's a 10-volt gain across the battery, there's a 10-volt drop across that resistor. A 10-volt gain across the battery, there's a 10-volt drop across that resistor. All right, that's what the loop rule has to yield for resistors that are connected in parallel. Now the junction rule, here's where we really get to a kind of more legitimate application of the junction rule. This thing here is a junction. Junction is where something comes in, multiple things come out, like in, out. Or down here, we have in, out. So we call this like a I in, I out, I out. These are currents in, this is a current out. The junction rule says that the net current in to any location and the net current out have to be the same thing. All right, whatever number of coulombs of charge per second get to this point, that same number of coulombs per second must leave that point, because if they didn't, where'd they go? Or if there's more that left, where'd those extra ones come from? All right, so this says, the junction rule says, well, that I total equals the sum of I1 and I2. These currents might be the same, but they don't have to be the same. What does have to hold up is that the total amount of current in the circuit has to be the sum of the 2 currents in each, or the sum of the currents in each of those branches. Okay, now we can rewrite this junction rule statement using Ohm's law, where Ohm's law says I is V over R. So I total is V total, I call that V battery, over R total, I call that REQ. I1 is V1 over R1. I2 is V2 over R2. But remember, what's true about these voltages? Well, they're all the same. So every one of these terms can be divided by the same common factor. And what we get is this expression for equivalent resistance for resistors connected in parallel. And that's that the equivalent, well, really that the inverse of the equivalent is the sum of the inverses of however many resistors you have connected in parallel. All right, so similar to what we did in the one of the first, or the slide a couple of minutes ago, we can say that this circuit behaves, at least very generally, like a circuit with a single resistance REQ. And again, imagine if we knew what that REQ was and we knew what the total voltage was, well, we could find the total current, V battery over REQ. And then we could say, all right, well, I know the total current, and then, oh, well, I know the drops across these because I know this. And then, so we can, in a lot of cases, really start our problem-solving process by applying this rule about how to find equivalent resistance for resistors connected in parallel. Okay, people are pretty good about this. People are pretty good about this. The problem is people just want to apply this to the series case, but it's definitely not the same in the series case. So yeah, does it take some doing to keep these things straight? It does, but that's your job as a learner. Okay, so let's apply to this case here where we have what we'll call V. Little tight. V battery. We'll call this R1. We'll call this, oh man, this is going to be tight. I'm going to do this. Nah, it's not going to help. Well, we'll just, I'm not going to draw all the different meters. Let's see. I've got our values of resistance. Let's go through the process of finding the equivalent resistance. So that looks like this. Well, 1 over this equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. So 1 over the equivalent resistance is 1 over 5 ohms plus 1 over 30 ohms plus 1 over 10 ohms, which is not 1 over 45 ohms. That's not how adding fractions works. So how do you add fractions? Well, you look for a common denominator. And in this case, our easiest common denominator is 30ths. So this is 6 30ths plus 1 30th plus 3 30ths. This says that 1 over REQ is, well, 10 30ths, because we can add those numerators. That's not our answer. That's not the equivalent resistance. That's the inverse of the equivalent resistance. Notice how those units of ohms are in the bottom of that fraction. This says that REQ, we take the inverse of both of these things. If 1 over REQ is 10 over 30 ohms, then REQ is 30 ohms over 10, or 3 ohms. So this is odd. It's a little bit odd that, I mean, it seems to make a bunch of sense that when we have resistors connected in series, we get more total resistance than any one of the individual resistors. Sure we do, because they're each limiting the flow of electrons. But here, notice, our equivalent resistance is less than any of the individual resistors, less than even the smallest. And why is that? Well, it's because even though each branch has its own resistance, each branch has the ability to carry current. And so the more branches we have, even if they have resistance, the more branches we have, the more current carrying capability we have. And the more current carrying capability we have, the less resistance the circuit has in total. So that's a little bit contrary to what you might think. But again, more resistors in parallel means less total resistance. Okay, well, notice now we have, there's two things we could do from here. One is we know if there's a 9 volt gain across the battery, well, here's a single loop of current that must have a drop equivalent to that gain. So V1 is 9 volts. You could say negative 9 volts, but we're worried more about the magnitude of that voltage. All right, here's a separate loop with a 9-volt gain and therefore a 9-volt drop. And so on and so on. The third voltage is also 9 volts because those resistors are all in parallel. They almost have the same voltage. And then Ohm's law allows us to find these currents where we can say, well, I total is V total, which we call V battery, over R total, which we call REQ, and 9 volts over 3 ohms is 3 amps. Well, I1 is V1 over R1, 9 volts over 5. Ooh, what's that, 1.8? Sure, 1.8 amps. 9 volts over 30, what am I, math major? So I2 V2 over R2, 0.3 amps. And then I3, come here, I3 V3 over R3, 9 volts over 10 ohms gives us 0.9 amps. Gee, I hope we're right. Who knows? I guess we'll never know. Oh, well, look, we can tell, right? Notice, if we add each of these currents, 0.9 volts and 0.3 volts is 1.2 volts. 1.2 volts and 1.8 volts gets us 3, what did I say, volts? Amps, gets us 3 amps. And that's good because that says the current that comes into this point equals the current that leaves that point. And that's an application of the junction rule. Okay, so if we know the physics, then we can be sure that we've gotten things right. This is it's rare, you know, even if you have a good understanding of physics, lots of questions are still, if you solve a problem, it's not always very easy to know if you've gotten it right or not. These are not that way. These, you know darn well if you've gotten it right, if you know the physics. All right, you have a way to check that you're right or not. Okay, so applications of the junction rule. Here's the junction rule about current. Says the current into a point must be equal to the current that leaves that point. All right, here's an application of the loop rule, which says around a single loop of current, the net increase in potential, or the net voltage gain, equals the net voltage drop. Okay, and you know, this kind of really lists all the things we need to know about voltage and current and resistance for both resistors that are connected in series and in parallel. So there are, for my kids' reference tables, the New York State Regents reference table has that stuff listed, but it wouldn't kill you probably to make yourself a little reference guide of your own. All right? Okay, adios.